In this lecture, I'm going to discuss finitely generated modules and their relationship with the ascending chain condition for modules, which is also known as the Noetherian condition. So let's start with finitely generated modules. So we'll take R to be a commutative ring. And we define an R module M to be finitely generated. So M is an R module. If you can find a finite number of elements of M that generate it, in the sense, if there exist elements M1, M2, Mn for some finite n, such that every element M in M is of the form M is equal to A1 M1 plus A2 M2 plus An Mn for some elements A1, A2, An in R. For example, if R is a field, then R modules are just vector spaces over the field. And a finitely generated R module is just a finite dimensional vector space over the field. And if you want an example of an R module that's not finitely generated, you could again just take R to be a field and take an infinite dimensional vector space over the field. Now, a very useful property of R modules that we will use later on is the following. So let's put it down as a theorem. So suppose M is an R module N a submodule of M, and suppose we know that N and M mod N, the quotient module, are finitely generated, then we can conclude that M is also finitely generated. The proof of this is not very difficult. You just write down generators of N, generators of M mod N, and somehow using them you construct a finite set of generators for M itself. So firstly you write down generators. Let U1 up to UR be generators for N, V1 dot 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 Vs generators for M mod N, and now we'll put these together to construct a generating set for M. Now the problem is that these V1, V2, Vs, they are in the quotient space M mod N, they're not in M. So what we'll do is we'll just lift them up to M. So let Vi tilde in M be such that Vi is Vi tilde plus N. So it's the image, Vi is the image of Vi tilde in M mod N. Then I claim that this set, you take U1 up to UR, and then you take V1 tilde up to Vs tilde. This generates M. So what do I need to show? I need to show that given any element M of M, I can write it as a combination of these things multiplied by scalars. So a linear combination of these elements. So take any given any m in M, let so its image in M mod n is M plus n. Okay, so this is an element of M mod n, and this because this v1 v2 vs generate M mod n is of the form M plus n is of the form a1 v1 plus as vs. Okay, and so that means that M is of the form a1 v1 tilde plus as vs tilde plus some element n of n. But then this element n is in n, so it can be written as, so this is for some a1 as in R, and this n can be written as a1 as vs tilde plus b1 u1 plus br ur for some b1 br in R. So at the end of the day, we've written M as a linear combination of the vectors, the module elements v1 tilde up to vs tilde and u1 up to ur. So a corollary of this is if M and N, well, it's rather a special case, if M and N are finitely generated R modules, then M plus N is also finitely generated. Of course, this may be much easier to prove than as a reducing it as a corollary of the previous theorem. You could just take a generating set of M, a generating set of N, and take their union, and that would be a generating set of M direct sum N. But this is I'll just explain the proof using this. How can we think of M plus N as a module with some submodule and some quotient module? The point is M is a submodule of M plus N, and M plus N mod M is isomorphic to N. So this submodule is finitely generated, this quotient is finitely generated. So by the previous theorem, M direct sum N is also finitely generated. It's a slightly different proof. And one observation about finitely generated R modules. So suppose our module M is generated by M1, M2, Mn. Then define an R module homomorphism so this Rn itself, R to the power n, which is R direct sum R n times. This is an R module, and we define an R module homomorphism from this to M by taking, so in this you let EI denote the element which is 0 at all places except for a 1 at the unit at the ith place. Okay, a coordinate vector, so to speak, by taking EI to MI. And what we have is that we'll call this map phi, and let K be the kernel of phi. Then M is isomorphic to Rn mod K as an R module, because whenever you have surjective homomorphism of R modules, then the target R module is a quotient of the domain modulo its kernel. A very useful condition in studying finitely generated R modules is that of Noetherianness. We've already seen the Noetherian condition for rings. Remember, a ring is said to be Noetherian if every increasing chain of ideals eventually stabilizes. So we can use the same idea for modules. So let's define Noetherian modules. So again, R is a commutative ring, and an R module M is Noetherian. It's said to be Noetherian if it satisfies what is called the ascending chain condition. Ascending chain condition. What is this condition? For every increasing sequence of modules, so for every set of submodules of M, maybe I should say sequence of submodules of M, say it starts with M1, which is contained in a submodule M2, which is contained in a submodule N3, and this goes on indefinitely. There exists a number n greater than or equal to 1 such that for all k greater than or equal to n, mk is equal to mn. So what we are saying is that this ascending chain of modules eventually stabilizes. So you cannot keep getting larger and larger and larger submodules indefinitely. And the relation to finite generation is quite straightforward to start with. We can show an easy lemma that if M is Noetherian, then M is finitely generated. Well, the way to prove this is by contradiction. If M is not finitely generated, then it's quite straightforward to construct an ascending chain that never stabilizes. Okay, so suppose M is not finitely generated. Okay, so obviously that means that M is not the zero module. So there exists some non-zero element x1 in M. Okay, so so let me introduce some notation over here. So given set of elements x1, x2, xn in M, I will define this angular brackets x1, x2, xn to be the set of all elements of the form a1, x1 plus, whoops, I don't need the summation here, an xn, where a1 up to an belongs to R. This is called the submodule of M generated by x1, x2, xn. It's the smallest submodule of M that contains all the elements x1, x2 up to xn. Okay. So now, since M is not the trivial module, I can take a non-zero element in M. And let's define M1 to be the submodule generated by x1. So it's just all elements of the form A times x1, where A runs over R. Now, M1 cannot be equal to M because M1 is finitely generated and M is not finitely generated. So then I can take x2 belongs to M minus m1. And now let's define m2 to be the module generated by x1 and x2. Now m2 is strictly larger than m1 because x2 is not in m1. Now m2 cannot be equal to m, so I can take x3 in m minus m1. m2 cannot be m because m is not finitely generated, but m2 here is generated by two elements. So now you get the idea, right? So now I take x3 in m minus m2 and I define m3 to be the submodule generated by x1, x2, x3. Proceeding in this manner, I get m1 properly contained in m2, properly contained in m3, so on, an infinite chain. This process will never stop because at each stage I cannot have that mn is equal to m, because m subscript n will always be generated by n elements, so it will be a finitely generated R module. So we get this strictly increasing chain of R modules which never stabilizes. So this contradicts the Noetherian hypothesis. Okay, so there's the first relationship between Noetherianness and finite generation. Okay, so Noetherian modules are finitely generated. Is that all there is to it? Is the Noetherian condition just the same as being finitely generated? The answer is no. The Noetherian condition is actually much stronger than the condition of being finitely generated. And one nice thing about the Noetherian condition is that it goes easily from modules to submodules. Okay, so here's something that's easy to see, that if M is Noetherian, N a submodule, then N is Noetherian. That's the very nature of this Noetherian condition, because so we want to show that N is Noetherian. So if you take submodules, an ascending chain of submodules of N, they will also be an ascending chain of submodules of M. So they will stabilize. So a submodule of a Noetherian module is Noetherian. However, it is not always true that a submodule of a finitely generated module is finitely generated. So this is where the Noetherian condition becomes very helpful. So let's prove the stronger result about Noetherian and finite generation. So theorem, and this is actually a characterization of Noetherianness. An R module M is Noetherian if and only if every submodule of M is finitely generated. Okay, so not only is M finitely generated, every submodule of M should also be finitely generated. Proof: if M is Noetherian and N is any submodule, so let's prove that the submodules are finitely generated. So suppose M is Noetherian and N is any submodule, then of course N is Noetherian. But we've just seen that every Noetherian R module is finitely generated, so N is finitely generated. Okay, so this side is easy. Let's try the other side. Conversely, so we have to show that if every submodule is finitely generated, then M is Noetherian. So let's start with an ascending chain. So suppose every submodule of M is finitely generated, and let's start with the chain M1, M2, M3, be an ascending chain. Now what you can do is you can take M infinity to be defined to be just the union n goes from 1 to infinity of Mn, and it's not difficult to show that M infinity is an R module. Okay, and all this is happening inside M, right? It's the union inside M of M1, M2. These are submodules in M. Okay, so it's a submodule of M, and so M infinity is a submodule of M. M infinity is finitely generated. So let's say M infinity submodule of M is generated by some elements x1, x2, xk of M. Okay, so each of these elements must be in M infinity. So xi belongs to M infinity, which means that it is in one of these Mn. So xi belongs to, let's say, Mni for I equals 1 to k, and just means that xi belongs to the max of n1, n2, nk. Let's call this number n. So all the xi's belong to M capital N, but then these xi's generate M, so that means that M capital N is equal to M. It cannot be any smaller because these elements x1, x2, xk, they generate M capital, they generate M, and they're all in Mn. So Mn must be equal to M because that's the smallest R module containing x1, x2, xk, which means that Mk is equal to Mn for all k greater than or equal to n. Maybe I shouldn't call this n, maybe I should call this L for all L greater than or equal. So here we've characterized Noetherian modules in terms of finite generation. An R module is Noetherian if and only if every submodule is finitely generated. We saw earlier that if M is an R module and it has a submodule n such that the submodule n is finitely generated and also M mod n is finitely generated, then the module M itself must be finitely generated. Now I claim that the same property holds for Noetherian modules as well. The theorem is that, so you have this commutative ring R, and suppose M is Noetherian. No, M is an R module, any R module. N is a submodule of M. And suppose we know that N and M mod N are Noetherian. Then I claim that M is Noetherian. In fact, this theorem will follow easily from the earlier result that I stated about finite generation and the characterization of Noetherian modules as those modules for which every submodule is finitely generated. So proof is, we will just show that every submodule of M is finitely generated. So yeah, suppose M prime is a submodule of M. Then we'll try to find a submodule of M prime which is finitely generated and such that M prime modulo that submodule is finitely generated. So take M prime intersect N. This is a submodule of M prime, and this is finitely generated because it's a submodule also of M, N. N is Noetherian, so M prime intersect N is finitely generated. And now I want to take M prime modulo N, but N is not a submodule of M prime, so I have to take M prime modulo M prime intersect N. Now the inclusion map of M prime into M, so you have M prime goes into M. It's just a submodule, so I just take the inclusion map, and I have M mod N, the quotient map, and I have the quotient map M prime mod M prime intersect N. And it's not hard to show that this is an injective map. That is, if something in M prime goes to 0 in M mod N, then it must lie in M prime intersect N. Well, that basically I've said it. So the only things in M prime that go to 0 in M mod N are those which are in N, so they are in M prime intersect N. So this is a submodule of M mod N, so it's also finitely generated. So this M prime has a submodule which is finitely generated, and the quotient by that submodule is also finitely generated. Therefore, M prime is finitely generated. This means that M is Noetherian because every submodule is finitely generated. So we've been proving all these technical results about Noetherian modules and finite generation. Now it's time to harvest the fruits of our hard work. The first result that we can prove is that in some sense the main result that we'll be proving from all this is that if R is a Noetherian ring, then every finitely generated R module is Noetherian. In particular, it will follow that if you have a submodule of a finitely generated R module, then that will again be finitely generated. Any submodule of a finitely generated R module is finitely generated. See, for Noetherianness, it's very easy to see that if a module is Noetherian, then every submodule is Noetherian. That's the Noetherian condition is like that. But for finite generation, that's not at all obvious. Why would a submodule of a finitely generated module be finitely generated? And that's not even true in general. But when R is a Noetherian ring, this always holds. And Noetherian rings abound, right? We've already seen lots of examples of Noetherian rings. All our Euclidean domains are Noetherian. All our principal ideal domains are Noetherian, in fact. Rings of polynomials in finitely many variables are Noetherian. Noetherian rings are everywhere, and this very general theorem gives us a very strong result. So how do we prove this? So the proof is now very simple. So first point is, what is the relation between R being a Noetherian ring and R modules? So the first point is that, so suppose R is a ring, then R can be thought of as an R module itself. How? Well, you just, if given M in R and R in R, so this is the module version of R and this is the ring R, then you just define R dot M to be Rm, the product in R itself, and you can check that R is an R module. This is sometimes called the regular R module. Okay, and then what are the submodules of R? Submodules of the R module are, so maybe I'll use, it's very awkward to keep saying the R module R, so I'll just this thing I'll write as R, and on the left I'll put a small r, saying that this R is acting on R, so R is a left R module. Submodules of the R module are, these correspond to ideals in R. Here we are working with commutative rings, so all ideals are two-sided ideals. And so R being Noetherian ring is the same as R as a left R module is a Noetherian R module. Okay. Now I claim that R to the n is a Noetherian R module. So this is just R as an R module, direct sum R as an R module, direct sum R as an R module. This direct sum is taken n times. And why is this true? Well, you can prove it by induction on R. This is R to the n minus 1 direct sum R. This has a submodule Rn minus 1 and the quotient is R. So this contains Rn minus 1 as a submodule and Rn mod R n minus 1 is isomorphic to R. So by this theorem that we proved that if you have an R module which has a submodule that's Noetherian and the quotient with respect to that submodule is Noetherian, then the R module is Noetherian. So it follows that R to the n is a Noetherian R module. Now finally, every finitely generated R module is of the form, is isomorphic to Rn mod n for some submodule n of Rn. We already saw this when we talked about finitely generated modules. You take, if there are little n generators, then you just take a homomorphism from Rn to your module, which take the ith generator to the ith copy in to the ith, take the ith coordinate vector in Rn to the ith generator in your module, and you'll get an isomorphism with Rn mod n. Now this Rn is Noetherian, so let's just we need a small result here. If M is Noetherian, and n is a submodule of M, then M mod n is Noetherian. This is easy because submodules of M mod n are the same as submodules of M containing n. Okay, so if you have an increasing chain of submodules of M mod n, then you just take their pre-images in M. That's an increasing chain of submodules containing n. Just if you have a submodule here S, then you just take it to Q inverse S, where Q is the quotient map from M to M mod n. So the Noetherian condition for M mod n is a special case of the Noetherian condition for M. Just apply it to submodules containing n. So now we know that R is Noetherian, we know that Rn is Noetherian, and we know that Rn mod n is Noetherian. So we conclude that Rn mod n is Noetherian, but every finitely generated R module is the form Rn minus n. So every finitely generated R module is Noetherian. So what we have is any submodule of a finitely generated R module is finitely generated. So that's the main theorem of this lecture.